Hello everyone, welcome to this special episode of Let's Learn Physics, the show where I explain graduate level physics textbooks to curious minds like you. Last time we looked at Chapter 3 of Classical Mechanics by Herbert Goldstein, but we skipped sections 10 and 11 which had to do with scattering. So I'm going to devote today to talking about scattering off a central force field in classical physics. I will say that although this is a very significant theory that is used in experiments of all kinds, and although I read the chapter a couple of times, I am not confident that I fully understand it. So if I get anything wrong, make sure to let me know in the comments. So first, what is scattering in physics and why is it important? Scattering is when two objects strike each other and bounce off. In some sense, it's like two pool balls hitting each other and bouncing off in different directions. In another sense, it's like one pool ball glued to the table and a bunch of infinitesimally small particles streaming at it from one direction and bouncing off at all angles. The closer the particle strikes to the center of the ball, the greater the angle it deflects at. In classical physics, particles are considered to be point particles, that is, to have zero size. A scattering system involves a stationary source of force and an incident intensity of point-like particles coming in all with the same direction and the same speed and scattering off that fixed central source. We can think about individual particles or we can think about a continuous flow. If the force is repulsive, the incoming particles bend away from the source, and if the force is attractive, the incoming particles bend toward the source. We can calculate and measure all kinds of things, which we'll get to in a minute. But first, why is scattering important? Well, it's extremely useful when we have a system that we can't see what's happening when the objects interact, but we can measure what angle they're coming in, and we can measure what angle they're going out. So particle physics experiments are almost completely scattering, as are experiments probing molecular structure of materials. Planetary slingshots, where a satellite goes around a planet to get a boost in its orbit, can be thought of as scattering systems. And I did a research project in undergrad with a professor who was studying scattering of dark matter flows around the sun and the Earth. So let's suppose we have a repulsive force centered on a fixed source. How do we set up our scattering diagram? Well, first we imagine that all the scattered particles are coming from the same direction with the same speed. So we draw an axis from the source to the side of the page that is parallel to the velocity. When they get close to the source, the force causes them to deflect into a different direction. The difference between the direction they come in and the direction they go out is called the scattering angle. The distance a particle starts away from the axis is called the impact parameter, which is related to the angular momentum and the energy by this formula. If the scattering force is strong at the center and weak as the distance increases, then the larger a particle's impact parameter, the smaller the angle it deflects. Unless the source has a finite size in which the particle will actually scatter less if it passes through the interior of the source particle than if it passes by the edge. This results in a cone on the far side of the source particle where the deflected particles have a maximum angle, and that cone is a caustic. It has infinite density. So when it comes to experiments, we want to know the relationship between the angle deflected and the impact parameter. That is, we want to know how much the incoming particle deflects based on how far away it starts from the axis. Calculating it straight up using the deflection angle is not easy, so we use a different angle. I haven't found a name for this angle yet, so we'll just call it psi. As an incident particle gets deflected halfway, it reaches a closest distance to the source particle. That distance is labeled Rm or Rmin. After that, it continues to get deflected the rest of the way. If we draw a line from the source across Rmin, the path of the scattered particle is symmetric about that line. That means the angle between Rmin and the incident trajectory is equal to the angle between Rmin and the outgoing trajectory. And those two angles plus the deflection angle equal 180 degrees, or pi radians. So the deflected angle equals pi minus 2 times this psi angle. Remember this angle differential formula from chapter 3? No? Well, we did talk about it in chapter 3. Well, if we integrate that from r min to infinity and rewrite the angular momentum in terms of the impact parameter, we can calculate psi, which means we can calculate the scattering angle. The last thing we can calculate is the scattering cross-section, which can be thought of as the size of the source particle. In the case of solid spheres bumping into each other, the scattering cross-section is just the cross-sectional area of the object. When it comes to point charges of central force, it's a little less clear what the scattering cross-section means. If we're talking about the area that any particle will be scattered by any angle at all, then the scattering cross-section is infinite. Because if we have a source of force, then any other particle anywhere in the universe feels at least some minuscule force from it. Pragmatically speaking, it makes sense to limit the angle that counts as scattering. I believe in my research I found a standard angle that is used as the boundary for what counts as scattering cross-section and what doesn't, but I forgot what that angle is, and I haven't been able to find it again. I imagine it's something like 1 or 2 degrees. So suppose we chose 2 degrees as our cutoff angle. There is an impact parameter that corresponds with 2 degrees of scattering. And if you sweep that impact parameter around, you get a circle that is the scattering cross-section for an angle of 2 degrees or more. Any particle that passes through that circle will scatter with 2 degrees or more. And so, and this is the part of the video I am not certain about, we can talk about the size of the source particle based on the scattering cross-section at the critical angle cutoff. It's also worth noting that because faster particles scatter less, the scattering cross-section also depends on the velocity of the incoming particles, which makes this part even less certain to me. The velocity is a function of the energy, and especially under relativistic scattering, it is the energy that sets the relationship between the impact parameter and the scattering angle. One famous example is the Rutherford scattering cross-section, the cross-section of an atomic nucleus, based on the famous gold foil experiment where Rutherford students discovered that atomic nuclei are much, much smaller than the size of the total atom. Rutherford scattering uses the electrostatic force, which is a 1 over r squared force, and in 1 over r squared forces, the impact parameter is related to the scattering angle with this equation, and the scattering cross-section is related to scattering angle with this equation. Section 311 takes the system to be a little bit more realistic in acknowledging that in any real situation, the source particle is not fixed, but it experiences recoil from the other particles scattering off of it due to conservation of momentum. The scattering angle we've been talking about so far is the angle in the center of mass reference frame. We use an uppercase theta for the center of mass reference frame and a lowercase theta for the lab frame, or the frame that we actually measure particles in. In the center of mass reference frame, both particles start out moving and both particles scatter at the same angle, no matter what their relative masses are. To transform into lab coordinates, you use this equation, where that rho is this, where that mu is this. No one said it was super easy. The difference in the speeds between the two particles in the center of mass frame is given by this equation, where v is the relative speed in the lab frame after the collision. For an elastic collision, that is, kinetic energy is conserved, the relative velocity before is equal to the relative velocity after, and rho is just equal to the ratio of the masses. For an inelastic collision, we can calculate the difference in kinetic energy, which is given by naturally what you'd expect. Transforming the scattering cross-section into the lab frame involves a big scary trig function that I haven't even bothered to write in my notes because it would just look awful and isn't worth putting in the video. If the scattering is an elastic collision with equal masses, like 2 protons or 2 electrons, the lab frame scattering angle is just the center of mass scattering angle divided by 2, and the scattering cross-section transforms like this. And finally, classic scattering of elastic collisions operates just like standard conservation of momentum and conservation of energy that we teach in freshman physics classes. So that was scattering in classical physics, according to the textbook by Herbert Goldstein. I hope you got something out of this video, or at least found it mildly interesting. If you think this type of educational analysis is valuable, you can support this channel on Patreon. Please let me know what you think in the comments section. Don't forget to like and subscribe for more Let's Learn Physics. Thank you for watching. I'll see you next time.